Hello, my name is Michael Gelke, a technical advisor at ZMJS Abstract. Today we'll be discussing the fundamentals of MathEngine, our open source logic framework. This talk will cover how models are built in MathEngine, focusing on shape types as the building blocks of models. Before we dive into the technical details of what a model is, let's discuss why we'd want a formal model. The answer is simple. We need a way to define what terms in our type theory mean. There's two approaches to defining a theory, with the first being a synthetic definition. In this approach, terms are defined by construction rules and operation by rules on how to manipulate those constructions. This approach stands on its own without relying on anything else, like the rules of a game. The second approach is to define a semantic model. In this approach, we define our terms as familiar objects and our operations in the new theory map to operations on those familiar objects. In a semantic model, we define the new in terms of something familiar. To put the key idea more formally, a model is a map from terms in the theory to a class of familiar objects with accompanying rules for how to translate operations on those terms into operations on those objects. So let's explore what a model looks like for some familiar types, basic shapes. We'll start with the point and work our way towards more complex shapes. The structure of a point isn't particularly interesting, nor is the diagram. But I'll take this moment to call out one technical detail in our diagrams today. Most of the operations will be represented as arrows. However, there is an identity map on each vertex that is unpictured, or if you prefer, going nowhere from that point. So you can think of that purple dot in the diagram as representing some kind of identity on A. This will make more sense in a moment when we introduce other arrows and colors. So the second type, building on the point, will be the interval. The interval has three parts, and they're the ones you're expecting. An indexed range in the middle with two endpoints, one on one extreme, which we'll call I sub 0, and one on the other extreme, which we'll call I sub 1. We require that these points match up in some sort of way, right, where the endpoints actually correspond to the ends of the range. So we'll look at the construction of the interval not as a shape, but as a diagram of the pieces involved. That diagram is the first time we're seeing arrows, with the inclusion map going from A down to the interval I, or the range I, and a restriction map from that range back to the endpoint, and similarly for B. For our next example, we'll look at the loop. And as you're expecting, a loop is very similar to the interval, except for the added condition that the two endpoints are the same, A equals B. And in our diagram, we can see that we have the same structure, with the additional equality relationship between A and B. So that's all well and good, but you might naturally be wondering, why are we interested in defining these shapes in this unfamiliar way where they're abstract types? What are we going to use this for? So we're going to explore an example of why that can be a useful thing to do by asking ourselves the question, why is it that a circle represents a clock? Let's approach the problem by fitting our clock data to the structures we have defined before. The range is going to be the full range of clock data, all the possible times as some kind of index sequence. And while I've listed only a finite number here, this approach works for continuous sequences of time. Then our A is going to be the first value, 12. Our B is going to be the last value, 12. And our technical conditions are more or less all satisfied by knowing that 12 equals 12 because equality is reflexive. And if we look at what these pieces mean, we've actually built a loop, right? We have every one of the pieces that is required to define a loop. And so the answer to our question, why does a clock fit on a circle, is that both the circle and the clock are instances of the loop type. They share the same structure. So let's take a moment to recap. The reason why we want a model is that we want to translate our type theory into something familiar. And we do that by finding a familiar structure which faithfully represents our type theory, such as construction diagrams. We've gone through a few basic examples on how to translate familiar shape types into these diagrams, and a short excursion into why we'd be interested in using these types more generally than just sort of geometric applications. But the diagram approach has limitations. Namely, while it's easy for us to visually inspect these diagrams and reason about them, it can be difficult to work with them on computers. So the question arises, how do we create a more computational model for MathEngine? In graph theory, one approach is to translate your graph into an adjacency matrix for computation. We'll do something similar here, translating our diagrams into matrices which store the same data. We'll explain the formal definitions of operations in our next talk, but for now, we'll explore two examples to get the flavor. The first is a product of two intervals is a square. Here we see the diagrams of two intervals and of a square. And in the diagram of the square, we omit the restriction maps, but they're implicitly there for each inclusion map. The most interesting feature of this is that we can see for each of the points on our left-hand interval, there's a copy of the right-hand interval in the diagram. And a third one for the range, which I'm going to call a higher dimensional one. And we can see that much like the V shape in our interval diagram, there's this V shape connecting the three sections of our square diagram. And so this diagram is, in some sense, capturing that the square is an interval of intervals. This is the matrix representation of those same diagrams, where each of these matrices is corresponding to one of the diagrams. And you can see that every object has an identity along this diagonal, and that we're replicating the same inclusion maps. A is included in I, B is included in I, and I can be restricted to either A or B. And we can see in the square, we again have three copies of the interval diagram. And if you sort of squint and pretend you're zooming out a little bit, you can see that these inclusion and restriction maps off to the side are in the places we would expect them to be for an interval. And so our matrix representation has similarly captured this interval of interval structure that we believe should be in a square. But that a square or product of intervals works in our model isn't too surprising. What happens when we try to compute something that we didn't explicitly encode? For our second example, we'll explore the difference of a cylinder and square. We have the same diagram for a square as before, and the cylinder is that with some extra equalities to glue it shut. One for each interval in the square diagram. This example shows something that is easy visually, but might be hard to compute without an efficient representation of the diagram itself. The square matrix is the one we saw previously, and the cylinder matrix is the same, except that it has loops along the diagonal, and so represents an interval of loops rather than an interval of intervals. And so the question we're asking is, what is the difference between an interval of loops and an interval of intervals? And the difference of that is 3 pairs of equality relationships, one for each loop in the cylinder we're closing. One at each end, this one in the top, and this one in the bottom. And then one that closes the body of the square on itself, this one in the middle. So let's summarize the more abstract things that we've dealt with. Why do we want a model? To translate our type theory into something familiar we know how to work with. And we do that by finding a structure that faithfully represents our type theory, the model. As we've discovered, we can represent types as diagrams. To make that more computational, we can represent those diagrams as matrices. We saw that shapes are faithfully represented that way, and further, we can reason about them, as in the case of the difference between a cylinder and a square. So now that we've worked through the abstract version, let's see how this is implemented in MathEngine. There are 2 types of data in our model, objects and arrows. An object has a name, or index, and the associated data, dimension in the case of shapes. An arrow is composed of the starting and ending objects, and the associated data, such as the type of relationship. For some technical reasons related to the matrix encoding, we also need a type of arrows that represents no arrow existing, called none in our framework. A model is then a collection of objects and arrows, with size being the number of objects and complexity being the number of arrows. But there's something a little strange in this definition. We've been discussing diagrams and matrices. So what do we mean by image or marking an image? If we look at the image type, we can see the answer. Image is actually a sparse matrix type, where we store the arrow data at appropriate indices. So why the change in terminology? That's to highlight that in MathEngine, our models aren't really using the linear algebra structure associated with matrices. We're just using them as arrays of data. That's closer to a digital image. And when we discuss operations on models, we'll see that many of the operations look like image transforms. So how do we encode shape types into this model framework? The types that we've been discussing earlier. Well, there's 3 operations we're going to discuss now on an abstract shape. First, we can add a cell to the model with a particular dimension for that cell. An example would be 0-dimensional cells are the point, 1-dimensional cells are the ranges we've been discussing, 2-dimensional ranges, and so on. Second, we can glue one cell to another, which in our framework creates an inclusion one way and a restriction the other. This is typically used to attach lower dimensional cells to higher dimensional cells in the way that we might want to attach a point to an interval. Finally, we can equate 2 cells, which creates an equality map in both directions. This would be how we close the loop diagrams. So let's look through the three examples of shape types we discussed earlier in this talk, saving the square and cylinder for next talk when we discuss operations such as the product of two shapes. Again, for the point, there isn't much structure. A single cell of dimension 0, which we label star. For the arable and loop, the story is slightly more complicated. We have 0-dimensional cells, A and B, which here we label start and end. We also have a 1-dimensional cell for I, which we label middle. And we glue each endpoint onto the interval. As before, the loop is different from the interval in a single way. That extra relationship where we equate start to end. And that will cover our technical content for today. To read more details, our white paper, Shapes as Digital Images, is available on our website. To get a preview of our next talk, our second white paper, Shape Types Have Operations, is also on our website. Looking ahead, we have a second white paper on shape deconstruction upcoming, followed by one on implementing groups using the same digital image framework within MathEngine. We hope you've enjoyed this introduction to shape types and model building within the MathEngine framework. Please feel free to reach out with any questions or comments. And our MathEngine implementation is available on GitHub, including code used to generate our white papers. Thank you.